Carrying on the conversation. So just to kind of summarize and recap, we've been speaking about membranes. We started with a review of the structure. We then talked about transport. So we began speaking about the chemical and electrical forces that govern the movement of particles across the membrane. What we're going to move on here to speak about now is the rate of movement across the membrane. So what are the factors that influence how fast particles move across the membrane? And we're going to talk about three distinct factors that influence passive transport. And then later on, we'll move on to talk about some factors that influence active transport. Okay. So the rate of transport really is how fast particles are moving, specifically how fast they're accumulating on one side or the other. So when we think about transport, when we think about transport, we're thinking about the net flux of particles. So particles could be moving, as we can see in the top scenario here, the illustration A. We can have an equal distribution of particles across the membrane as we do in this container, where we do see movement. So we see one-way flux happening from one side, one-way flux happening to the other side as well, but there's no net transfer of molecules, okay? When we speak about the rate of transport, we're speaking about the rate of net movement, okay? So if we look at the bottom here, because we now have a higher concentration of particles inside 2 moles, and a lower concentration of particles on side 2, we now have established a gradient. And so we're going to see flux, but we're going to see net flux. So net flux means that there will be an accumulation of particles on one side or the other. And we can see that because there's a higher concentration on side 1 and a lower concentration on side 2, the net flux will be in the direction of side 1 to side 2. Okay. And what that really means is that when we look at both direction of movement of particles, the one with the greater force, which is created by this gradient, is the one that has the overall accumulation. So particles are moving to the side 2 and staying there. That's what we mean by the net accumulation of particles from one side to the other. When we have no net accumulation of particles, this is called diffusional equilibrium. And so although we do see particles kind of moving from side to side, they're at equilibrium, and so there's no net accumulation. All right, so particles will move according to the concentration gradient until they get to this diffusional equilibrium. This is what we mean by the force or the chemical gradient or the chemical driving force that wants to bring particles to equilibrium. It wants to move particles from side to side until there is an equal concentration on either side. And at that state, we're said to be at diffusional equilibrium. Okay. And so the rate is really how fast that is happening, how fast we go from net movement to being at diffusional equilibrium. So let's kind of recap here. We've got passive transport. We said it is spontaneous. We said that it liberates energy instead of requiring energy. We also compared it to being a downhill type of movement. And so we're going to really talk about some of the factors that influence the different types of passive transport. So we've got 3 different types of passive transport. We've got simple diffusion, and simple diffusion doesn't require anything. It's simply moving across the membrane. We think about things like oxygen, we think about things like carbon dioxide, we think about uncharged particles, lipophilic or hydrophobic, or nonpolar particles that can go right through the membrane without any type of facilitation, without any transporters, without any channels. And so that's what we call simple diffusion across the membrane. The second type of passive transport is facilitated diffusion. That's going to require a protein in the membrane, which we call a transporter. We'll talk about how that differs from the other two. And then the third type is diffusion through channels, which also requires something in the membrane, but instead of a transporter, it's an actual passageway or a pore, which we call a channel. So these are the 3 types of passive transport that we're gonna discuss here. So again, kind of breaking down simple diffusion here. No membrane proteins are required. This has to be a substance that can go through that lipid bilayer. So again, calling on remembering what the lipid bilayer looks like because it's an amphipathic structure. Anything that goes through the center of that bilayer must be nonpolar, must be lipophilic or hydrophobic, okay? We're thinking again about oxygen, carbon dioxide, or things like nonpolar, non-charged particles. Some of the factors that affect the rate of movement through the membrane, the rate of simple diffusion, are the magnitude of the driving force, so how strong the force is, the membrane surface area, how much surface area exists for transport to occur across, and then thirdly, the membrane permeability. So how likely is this particle to go through the membrane? This again determines on the type of particle, the shape of the particle, the size of the particle, and then the charge and so on. So the strength of the driving force, the amount of surface area that exists for transport, and then the permeability of the membrane to the molecule in question. So let's start by looking at that first factor, which is the magnitude of the driving force, and kind of illustrating what that really means. So we're starting off by looking at factors that affect or influence the rate of simple diffusion. The first one that we're going to illustrate here is the magnitude of the driving force. Okay. And so let's take a few scenarios here at the bottom. So we've got 3 containers. Say container A, container B, and container C. Each of them are separated by a semi-permeable membrane. Okay, and the membrane is permeable to the particle that we're speaking about. That's really important to understand. So we've got a membrane that's separating 2 sides of this container, and the membrane is permeable to the particle that we're discussing. On one side, let's start with scenario A or container A. On one side of this membrane, we've got 1 mole of particles dissolved in this solution. Okay, so that's our concentration on the left. On the right, we have 0 particles dissolved. So it's basically pure water. In container B, we've got, let's say about 0.8 moles of particle dissolved in this solution. And on the second side, we have slightly less, about 0.5. Okay. And then in the third container, we actually have an equal distribution of the particles. So 0.5 on one side and 0.5 on the other. And so we can compare the rate of diffusion across these 3 containers by looking at the magnitude of the force that exists. And remember, when I talk about the magnitude of the force, I'm really talking about the strength of the concentration gradient. So because we have a stronger gradient in container A, we have a stronger magnitude of the driving force here, okay? Which is indicated by this large arrow. We have a bigger gradient, which gives us a bigger magnitude of the driving force. And so because we have this larger gradient and this larger driving force, we automatically have a faster rate of transport. Okay. In container B, we have a smaller gradient, right? We have 0.8 on one side, 0.5 on the other side. So we don't have quite as strong a gradient as in container A. So we have a smaller magnitude of the driving force, indicated by a smaller arrow. And so we also will see a slower rate. So we got a smaller gradient, which equals a slower rate of transport. Okay. And then finally in scenario C here in this container, because we had an equal distribution of particles here, we have zero gradient. Okay, what we see is that one-way flux. So we've got particles moving to this side, particles moving to that side, but there's no net accumulation on either side. So although we have one-way flux, we don't have a driving force and we don't have a gradient. So we have a zero rate of transfer of these particles. So no gradient equals no net flux of particles. Okay, and we called this diffusional equilibrium. Oops. Okay, we call this diffusional equilibrium. So although we had one-way movement, there was no net flux of particles from one side to the other. So we can see here as the gradient gets smaller, the strength of the driving force gets smaller, and then the rate of transport gets smaller until there's no net movement or no net flux at all. So we have zero movement essentially, okay? So this is how we can kind of illustrate that the magnitude of the driving force is directly proportional to the rate of transfer with simple diffusion, provided that the membrane is permeable to the particle that we're speaking about. Okay, that's a really important point to make as well, that the membrane must be permeable.